Now let's look into the one of the dimensionality reduction algorithm, dimensionality reduction method, which is principal component analysis. Principal component analysis is a popular and widely used dimensionality reduction technique that aims to transform high dimensional data into a new lower dimensional subspace while retaining as much of the original data's variance as possible. It achieves this by identifying the principal components, which are orthogonal directions along which the data varies most. Let's see a definition, explanation of principal component analysis PCA. So, the most important, let's break down the key concepts of PCA. So there are two key concepts which has to be understood under PCA, which is principal components, the first one. So what is principal components? Principal components are the new transformed features obtained from the original data. Each principal component is a linear combination of the original features. So principal component is nothing but these are the new transformed features obtained from the original data. So each principal component is a linear combination of the original features. This is what is the principal component. Another key concept under which is variance. So variance measures the spread or dispersion of the data points around the mean. In PCA, we seek to capture as much of the variance in data as possible with fewer principal components. So that's what is the variant concept under principal component analysis. Now let's look into the working principle of PCA, how it works. So the major things that we have to understand are standardization, covariance matrix, eigenvectors, and eigenvalues, principal component selection, projection. Okay, so out of them, let's begin with standardization. What is standardization? The first step in PCA is to standardize the original data by subtracting the mean and dividing by the standard deviation for each feature. This is essential to give all features an equal scale and avoid any dominant influence from features with larger magnitudes. That's what is standardization. This is very very important because uh, if the if you have a larger magnitudes in your data set, that may have a dominant influence on the target variable. So to avoid that, so this standardization is essential to give all features an equal scale and avoid any dominant influence from features with larger magnitudes. Then we will move on to the covariance matrix. Covariance matrix, PCA calculates the covariance matrix of the standardized data. Okay, so the covariance matrix represents the relationships and dependencies between the features. That's the another second step, which is covariance matrix, or PCA calculates the covariance matrix of the standardized data. Once the data is standardized, then it's time to do the covariance matrix calculation. And the next step is mathematics, pure mathematics. It's eigenvectors and eigenvalues. PCA decomposes the covariance matrix to obtain its eigenvectors and eigenvalues. Eigenvectors are the directions of the new feature space principal components, and eigenvalues indicate the amount of variance captured along these directions, and that's what is eigenvectors and eigenvalues. So eigenvectors, basically here PCA decomposes the covariance matrix to obtain its eigenvectors and eigenvalues. So eigenvectors are simply the directions of the new feature space, which consists of a principal components, and eigenvalues indicate the amount of variance captured along these directions. So that's it. Okay, this is one is basically your components, principal components will give you the combination of principal component will give you eigenvectors, and for each eigenvector we'll calculate the eigenvalue. So, and finally we will move on to the next step. From eigenvector and eigenvalue, next we will move on to the principal component selection. Okay, so PCA sorts the eigenvectors based on their corresponding eigenvalues in descending order. The eigenvectors with the highest eigenvalues capture the most variance and become the principal components. So the number of principal components chosen determine the reduced dimensionality of the data. That's the next step, is to do the principal component selection. Then the final step is projection. The original data is projected onto the new subspace spanned by the selected principal components. Each data point is represented by its lower dimensional coordinates in the principal component space. So now let's look into the mathematical equations of PCA, various formulas that we use in PCA. So the first one is standardization for each feature. Standardization for each feature, the standardized value is calculated as z is equals to x minus x bar whole divided by sigma. So where x is the original value or individual value, and x bar is the mean of the sample or mean of the variable or feature data, and the sigma is the standard deviation of the distribution or the standard deviation of the whole that respective variable. Okay, so this is how you standardize. Here you can see that our first step is to do the standardization. So standardization can be done using z-score. So z-score standardization or standard normal distribution, converting into that. Anyway, anyhow you can say either standardization or standard normalization. Then next, for the step 2 covariance matrix, the covariance matrix of the standardized data is calculated as following. So if you have three variables, basically, so it's going to calculate the covariance between each. So the covariance matrix is a P by P symmetric matrix, where P is the number of dimensions that has as entries the covariances associated with all possible pairs of initial variables. For example, a three-dimensional data set with three variables. Here, let's take x comma y comma z. Okay, a three-dimensional data set with three variables, then the covariance matrix look like this, a 3 by 3 data matrix of this form looks like this. So covariance of x comma x, x comma y, x comma z, same y comma x, y comma y, y comma z, and z comma x, z comma y, z comma z, and this is how your covariance matrix looks like. Okay, so once you are done with covariance matrix, then what's next to do? Obviously, next is to calculate the eigenvectors. You have to find out the directions and then eigenvalues to check the magnitude. Basically, eigenvalue is it's fundamentally eigenvalue is a value which is nothing but the amount of variance captured in those directions. That's it, in those directions. Okay, now let's see. And obviously we have to go for the highest variance. So now it's time to calculate the eigenvalues and eigenvectors. The eigenvectors we call it as a nu, and their corresponding eigenvalues lambda of the covariance matrix can be calculated with the following equation. So C is our covariance matrix and V is eigen vector, lambda is eigenvalue and V is eigenvector. So with this multiplication of these two matrix and multiplication of these two, let's take and we can get the value of we can get the eigenvalues, lambda values. Okay, this is pure mathematics. You can do it. You would have done it in engineering. Still, here we can use softwares to just get these values. Okay. Now these eigenvectors represent the principal components, and the eigenvalue signifies the amount of variance captured by each principal component. So next let's move on to the algorithm working process. First one, as usual, as we have discussed earlier, uh, standardize the original data to have zero mean and unit variance. Then calculate the covariance matrix of the standardized data. Compute the eigenvectors and eigenvalues of covariance matrix. Then sort the eigenvectors based on their corresponding eigenvalues in descending order. Choose the top k eigenvectors, principal components that capture the desired amount of variance. And finally, project the original data onto the selected principal components to obtain the reduced dimensional representation. That's it. That's what is our algorithm working process. So now let's look into the applications and some of the uh, in fields where we can apply this PCA successfully. So what all we can do with PCA before we go into the real life examples. So applications, let's begin with dimensionality reduction. So PCA is primarily used for reducing the dimensionality of high dimensional data, making it more manageable for visualization, exploration, and modeling. This is the main application. Other than that, we can do noise. It can be used in noise reduction by focusing on principal components with high variance. PCA can remove noise and redundant information from the data. And similarly, we have data visualization. PCA is widely used for data visualization, especially when dealing with data in more than 3 dimensions. It helps visualize clusters, patterns, and relationships in lower dimensional space. And then last one is a feature extraction technique. So PCA is often used as a pre-processing step in machine learning algorithms to extract essential features and improve model performance. And that's what is so. As a data scientist, I highly use them in the following three applications. One is dimensionality reduction and feature extraction. By and large, we will be doing this in feature engineering and noise reduction sometimes too. Now let's take real life examples where exactly what type of tasks it can be handled. So real life, let's begin with image compression. In image processing, PCA is used to compress images by reducing the dimensionality of pixel values while retaining the most critical visual information. And face recognition. PCA is employed in face recognition systems to reduce the dimensionality of facial images and extract discriminative features for identifying individuals. Similarly, we have genetics. In genomics, PCA is used to analyze the gene expression data and identify patterns or clusters of genes related to specific conditions or diseases. And finance, when it comes to finance, in finance, PCA can be used for portfolio optimization and risk management by identifying uncorrelated principal components representing different asset classes.